Hey, g'day, it's Prezo. Thanks for stopping by the workshop today. Now, I'm starting a new workshop series. This is all about building a rear tool post specifically for parting off in a Colchester Student lathe. Now, before you turn off, this will work for anybody with a lathe that has a flat machine surface on the top of the cross slide. So as long as there's room at the back of that cross slide where you can mount accessories, it will work for you. And I guess the first question is, why do I want to do this? Well, parting off in the lathe is not my favorite activity. I seem to suffer from all sorts of problems when I do that, like tool chatter, broken tool bits, damaged stock, you name it, I've done it. And I guess you could put this down to maybe poor technique, or maybe a worn lathe, or just inappropriate parting tool blades and so on. But for whatever reason, I don't like doing it. Now, it's not just me though, lots of people have this problem, and I'm going to show you a little cartoon here. This came from the Model Engineer magazine in 1954. Now, the person that drew this cartoon was named Terry Aspen. Now, Terry was a regular contributor to the Model Engineer magazine. He also wrote a series of books on foundry practice for home workshop engineers, and he was a very talented illustrator and cartoonist. But this little cartoon here will show you all of the stereotypes associated with parting off in hobby type lathes at home. Now, at the moment, I'm this guy, but I desperately want to be this guy. That's right, I want to be able to part off a bit of 4-inch stock, sipping a glass of Chardonnay and standing on one leg. If I could do that at home here, I'd be a happy, happy camper. So as you can see, it's not just me, a lot of people have this problem, and often it's associated with small lathes that lack rigidity. And in my case, I don't have that. I've got quite a large lathe for a home workshop, but I still have a problem with it. So I think that having a rear tool post is going to help me, and I did some research into this just a couple of days ago, and I'll tell you what, if you want to get into an argument online, just go to any home machine shop forum and start talking about parting off in the lathe. Now, you're bound to get a variety of opinions about why you might have a problem, and all sorts of people are going to weigh in with advice and they're going to tell you what you're doing wrong. But I did some research into this, and I want to show you on a little animation here why it's a problem and some ways of overcoming that problem. So let's have a look. What you can see here is an animation or a diagram showing a regular home workshop lathe. We're looking from the tailstock end toward the headstock. You can see here a workpiece mounted in the 3-jaw chuck, and you can see the direction of rotation that workpiece would make when you go to cut it with a parting tool. Now, I've got a cross slide down here. We've got a nut and a regular feed screw that would be used to move the cross slide backwards and forwards across the saddle of the lathe. Now, at the front of the lathe, where you'd normally mount a regular tool post and parting tools and regular cutting tools, we've got a compound slide. We've got the tool post sitting on top of that, and we've got a conventional parting tool mounted in the tool post. Now, at the rear of the cross slide, this is the thing that I want to make. What we have now is a solid tool post, no compound slide, and we've got an inverted parting tool mounted with its cutting edge along the center line of the axis of the lathe. Now, this is the configuration I want to make for my lathe. So the parting tool blade is inverted. What that means is that I don't need to change the direction of rotation of the workpiece in order to part off. Okay, so far so good. Now, let's consider what happens for a moment when we start to load up this conventional parting tool during a cut. Now, the force that's applied to the parting tool blade is basically downwards, and then the load is transmitted through the tool post, through the compound slide, to the cross slide. Now, this point here, this bullseye, is the fulcrum point. This is where everything is going to want to bend once the load goes on the parting tool. Now, of course, it's not just bending either. You've got clearance between the dovetail in the compound slide. You've got clearance at every interface between the tool post, the parting tool holder, and the blade itself. So all of those things add up to movement. But essentially what happens is it wants to pivot around this point. So let's have a look at what happens with that. I'm just going to zoom in a bit. So we're going to take the whole assembly, tool post, compound slide and blade, and we're going to apply that load around that fulcrum point. Now, straight away you can see what's going to happen here. The blade is going to pitch forward. It's going to dig into the workpiece, and then you get this sort of a positive feedback loop happening. So the more the parting tool blade digs in, the more it wants to rotate around that fulcrum point, and the worse the situation becomes. Now, if you've got a light lathe and you've got some clearance between the compound slide and the cross slide, or you've got sort of worn dovetails and that sort of thing, then you're going to find that you get not only this situation, but you're also going to get a lot of chatter. So things are going to start to bend and release and bend and release and so on. But you're going to get a catastrophic failure when this situation becomes worse. So that's what happens when you've got a regular conventional parting tool at the front of the cross slide. Let's have a look at what happens with the solid tool post mounted at the rear. So this time the cutting force is acting upwards at 90 degrees to the cross slide, straight upwards. When the load goes on now, notice what happens. So what you see now is that the tip or the cutting edge of the parting tool blade is pushed clear of the workpiece. And what happens is it becomes self-regulating. So the more load you apply, the more the tip or the cutting edge on the tip of the parting tool wants to move up and out of the way, and it never gets in that situation where you can have a catastrophic failure. So that's the difference between a conventional parting tool and a rear tool post with an inverted parting tool. Now, it's not just that either. There are other things that are going on here. So, for example, when you put the load on the inverted parting tool at the rear of the cross slide, it has the effect of lifting the cross slide up. Now that has the effect of tightening up the dovetail. When you have this situation at the front, as the load goes on the parting tool blade, it pushes downwards, and whatever clearance is existing between the dovetail and the cross slide is going to stay there, and it's going to allow lateral movement side to side. So again, the rear tool post has that sort of regulating effect where it tightens up the dovetail, and you've got less of an issue with side to side movement. Now, it's not just that either. With a solid tool post, you've got one less dovetail to worry about. With a compound slide, you've got two. So you've got one in the cross slide, one in the compound slide, and both of those have got clearance. But wait, there's more. Let's zoom in on the nut and see what's happening there. Now, you'd be aware that all nuts and screws which regulate the movement on your lathe have clearance. So in here you can see that there is some clearance between the screw flanks and the nut itself. Now, what happens when you use a conventional parting tool is that you're pushing the parting tool into the work. Now, let's have a look, see what happens when you push the screw against the nut. Now, what you see now is that all of the clearance is at what is effectively the front side of the cross slide. Now, what that means is that the whole nut can actually keep moving, and also the cross slide can keep moving closer toward the center of the workpiece because of this clearance here. Let's have a look what happens when we pull the tool into the work, and this is what happens with the rear tool post. So this time we're going to pull the screw. So now we've got the situation where the flanks of the screw are hard up against the flanks of the nut in the direction we're actually loading up the cross slide. So although the cross slide could still move toward the center of the lathe because of the clearance in the back of the screw, it doesn't want to because of the cutting action itself is pivoting the tool in the opposite direction. So in my view, this is a much more preferable position to be in, where we're actually pulling the tool into the work rather than pushing it. Okay, that's it. That's my takeaway from the research that I've done into this whole process and the physics of what's going on when you're trying to part off in the lathe. Before we start the actual machining process, I just want to show you some of the preparation I've done for this design. So this is a mock-up. This is made from partly 3D printed parts, partly wooden parts, and I have drilled and fitted all of the fasteners I need to check that the design works. Now I can bolt this down to the lathe, and I'll show you that, and I've been able to check that the center height of the tool bit is correct, that I can actually reach the center axis of the lathe with the tool bit in position, and then I've got clearance around all of the parts. Now I've done all of the drawings using Autodesk Inventor, and these are just the detailed drawings of each particular part. So that's the mock-up. Now the materials that I'll be working with are this big chunk here of malleable iron. Now this is going to form basically a solid tool post, and this particular part is going to be exactly the same height as my existing compound slide. Now there's a reason for that. I want to be able to possibly use this as a solid tool post. So instead of bolting at the back of the lathe, I can bolt it at the front and replace my existing compound slide with this particular part here. So that's malleable iron. These two parts here are steel, and they will form the actual tool post that holds the tool holder. So these are two individual parts that can be swapped out if necessary. Now this laser cut part here is showing me the shape that I want to be able to machine out of that bit of round malleable iron. So I don't want it to be round, I want it to be rectangular, and I laser cut this part here so that I could scribe around that when I go to saw off the curved edges. That's just going to act as a guide so I know where to cut. Alright, so there are all the bits. Let's just quickly go over the lathe. We'll bolt this part in position and we'll just see how it's going to work on the lathe. Just looking at the cross slide on my Colchester Student lathe here. This black casting on the back here has been added by me. Now this was to extend the cross slide so I could fit a glass scale and also a work light to the back of the cross slide. Now all of the holes you can see in the back of the cross slide here are from the factory. Now the 4 that I'm indicating here are for bolting down a factory fitted rear tool post. Now Colchester did make one. Here's an illustration from their catalogue. I've never seen one for sale in Australia. I guess they're available, but I tried and failed to find one, so that's why I'm making my own. The threaded holes in these positions here are 5/16 UNC, that's an 18 TPI thread, and I bought these screws specifically for holding down that tool that I'm making. So let's put the mock-up in position here and see how it looks. So I can actually bolt this down, and I've done that. I've actually checked to make sure that everything fits and everything's in position. And this is going to be made from that big chunk of malleable iron. Now the other two parts that I showed you before are going to sit on top of this part here. Now ideally what you would do is make all of this one part. So from here, the top surface, all the way down to the cross slide, that would be better as one part for rigidity. But I like the idea that I could take this off and rotate it through 180 degrees, and I could fit some other style of tool on this side here. So for example, an insert type parting tool. And at the moment I've got this high-speed steel parting blade sat in its own tool holder, and it's held down by 3 M6 screws here, and the parting tool blade is pinched down with 3 more M6 screws, so that when I tighten up these 3 here, it clamps the parting tool blade in its own tool holder. Now again, it's not ideal to have separate interfaces for all of these parts, but just for versatility, I like to do it this way. First step in machining this lump of continuously cast malleable iron is to face off both sides and bring it back to the same thickness as my compound slide. Now I've just spent the last 15 minutes trying to dial this in, and across these numbered points which correspond to the jaws I can get it pretty close, but in between there are lobes or lumps which I can't dial out. So that's about as close as I'm going to get. It's got like 1 millimetre of total run out across those lumpy bits. And I don't really want to machine this outer face here. It's just going to get belt sanded or linished later on. So that 8mm dowel pin is going to be used as a reference when we start machining the flat surfaces around the outside of this part. Don't really need to indicate in this side here because I'm just bringing it to thickness. I've just measured the height of my compound with a micrometer, 59.38, and this is about 64 at the moment, so I've got quite a lot come off that. So I'm just going to hog that off and then try and match that 59.38 off the lathe. About 4.3mm to come off, so I'm just going to fast forward through this and we'll come back when I'm really close. Now, unfortunately I can't get my micrometer in here in the back to measure this, so I'm just going to have to do it with the calipers. I've already set the caliper to the finished length of 59.38 and I've zeroed it out at that point. So it's looking like about 0.7 over size, yeah, about 0.7. So I'm going to shoot for that. Now, a couple of things here. I understand, and correct me if I'm wrong, but I had read that most lathes are designed to cut slightly concave when you're doing a big facing cut. The reasoning for that is that if you're going to make a part and it's got to fit up against another part, you want it to touch at the outer edge, not at the center. If it made a convex face, it's always going to rock at that center point. So measuring out here, I can get it to pretty close to my 59.38. Can't guarantee it's going to be that at the center. Now, I'm not really shooting for exactly the same height as my compound slide. What I want to have is something that I could swap out, so I can use this part instead of my compound slide and use this as a solid tool post at the front of the lathe. So if it's a couple of hundredths over or under, it's not that big a deal, but I want to get it very close. So I'm thinking 0.7 off where we are now, we should be pretty right. Sort of see how badly out of round that part is. It's unfortunate. Alright, that's pretty good. Just checking with my micrometer now, I'm at 59.4. I was shooting for 59.38, so 2/100ths over size. That's actually a good thing. What I could do is either scrape this in if I really wanted to, or I can take a fly cut across that in the milling machine to bring it back. But like I say, it's not that big a deal. Okay, what I need to do now is cut off the 4 round edges from this stock here, and it needs to come back to the same dimension as this piece of laser cut plastic. So I'm using this to transfer the shape that I want onto here, and then I'm going to use my metal cutting bandsaw to remove the waste. So I'm just going to slip that over the dowel pin, and we just scribe around that, and that's going to give us our lines that we need to work to. Now the bandsaw is not terribly accurate, so we're just going to use this to get rid of a fair bit of the stock. The rest can be done in the milling machine. I just need a target when I go to saw this, that's all. So there are my lines. This is my metal cutting bandsaw, and this won't fit in the main workshop. I've got this in a shipping container behind the workshop, and we're going to run this from an extension cord down to the back door of the shop. But it's a nice saw. I did have to do some repairs on this when I got it, but it's working quite well now. So what I've done here is I've put that piece of stock in the vise, and I've aligned a steel rule with the blade, and I'm using that to check the position of the cut. So I want the cut to be a bit outboard of the scribe marks that are put on there. So I'll go ahead and cut all 4 of these corners off, and then we can go back to the mill. You can see from that bit of waste, that's the top, this is the bottom here, so it's actually cutting a bit away from the line. It's not cutting perfectly square. It's probably a good thing. I can trim up the rest in the milling machine. And there's the end result, and you can see from these pieces of stock that some of them don't have parallel edges. This was the first one that I did, and these ones are better. And I can use this stock for making other things, but I knew that the blade was cutting a little bit off square and it was biased toward the outside of the stock. So I knew that the bottom edge of this material would be oversized compared to the top, which is sort of a good thing. And you can see here, if I put that template back in place, that I've got a good millimetre of stock all the way around to be removed, and that will happen in the milling machine next. And if you're wondering what these gouge marks are from, old dumbass here was talking to the camera and forgot to tighten the vise, so when I did the first cut, it just grabbed the stock and spun it out of the vise. So it's left a big gouge mark there, but that means that I can fly cut that now and take off that extra 0.02 of a millimetre. So yeah, a win. Okay, over the milling machine now, I'm going to square up this stock. I'm going to use touch DRO to do all of the offsets from that dowel pin that I put in the centre of that block. So we're going to move up half the distance we want, less the 4mm, which is the radius of the dowel pin. So I'm going to get the cutter in position, we'll zero out, and then we'll do that offset. The other thing I'm going to mention here now is that I have gone ahead and fitted glass scales to the Bridgeport. Now I did a series of videos on using the capacitive eye gauging type scales on this machine, and my original reasons for doing that were that they were easy to fit and they were relatively immune to chips and coolant. However, there was a problem. Now it's got nothing to do with touch DRO, it's all to do with the scales themselves. And it could also be that I have some sort of a noisy electrical system on this machine. But I would notice that occasionally when I was to start or stop the main spindle motor, the scales would misreport their position. Now at the end of the day, if you can't trust the scales, there's no point in having a DRO. So I bit the bullet and replaced all of the scales with glass scales. It was considerable expense to add to the machine, but I'm glad I did it. Since I fitted these, I haven't had any issues at all. Now, the glass scales are still going to be problematic with chips and coolant, but I've done the best I can with sort of shielding them and so on. This one on the quill is particularly hard to cover up, but there's not a lot of mess gets up there anyway, so I think I'm okay with that. So anyway, just thought I'd mention it because somebody's bound to spot it, and then I'll end up answering a million questions in the comments about what's going on. So there you go, I backtracked and I fitted glass scales. Anyway, let's get on and do this job now. It's probably a bit hard to see here, but what I've done is I've pinched a piece of shim stock between the insert and the dowel pin that I've got set in that hole in the base of this block. So everything's locked up in the vise there, and with the insert just rubbing on that shim stock, I can now zero out the Z on the touch the arrow, move up by half the width of this block, less the radius of the dowel pin, and that will give me my finished position for milling this surface here. So let's do that. So for this one we're moving 40.45 millimeters, and I'll zero out Z again, and then we'll just machine down to that position. Okay, it's at 40.45, so we'll zero out there, and then we'll just find our surface touch off, and we're just going to come back to zero. So I just swept that with an indicator to make sure I got this face truly vertical. So we're going to lock up the vise there, and we'll go ahead and machine this face on top. Just setting that insert on the shim for the last offset. You sort of feel the shim rolling backwards and forwards. So we'll zero out there. So look for 53.15. Zero there. And now we can take our last cut. think we hit that scribe line dead on, you know. Got the part sitting on some short parallels in the vise now, and I've found the exact centre in X and Y using an edge finder, and I'm set up exactly over that centre at the moment. So I've used that as 0, 0 on the DRO. So what I need to do now is to drill and counterbore these 4 holes. Now I've used the half dimension in X and Y. So in X we've got to go half of 95.25, so it's 47.62, and in Y we're going half of 55.56. Now these are unusual dimensions because they're originally in inches on the Colchester and I've converted to metric. Now one of the good things you can do at Touch DRO is you can log these positions ahead of time. So I've already done that on the screen, and I can come back and I can hit those same centres again and again. So rather than swapping out each operation for each hole, what I can do is go around centre drill all 4 holes, then I can drill all 4 and then counterbore all 4. And I can just keep coming back and hitting the same positions. So here we are at the moment, we're right over the centre of the part, and if I want to drill this hole first, all I need to do is touch that. And then you can see my coordinates are shown up here in X and Y. And we're just going to drive over to that position and we can drill that hole. So let's do that. So there we are. What we can do now is drill our first hole and then just work our way around, finding each hole position in turn and then doing the same operation in each hole. Alright, just need to be sure that's absolutely subsurface there, but I think we're pretty close. I sort of can't feel the head of that. I feel like I want to go a bit deeper. But anyway, you get the idea. I'll go around, just sort of hit them probably about another 0.25 deeper, just to make sure they're below the surface. Just got a bit paranoid about the tightness of that counterbore that I did before, and I've gone back with a regular 8mm metric counterbore, and I've drilled those 3 holes again. And now I've got a bit more clearance around the heads, and they're a little bit deeper. I think they were a bit too tight before. So I'm just about to do this last one up here. They're all done now, but I'll just lightly countersink these off camera and then we'll try it on the machine. You can see there that I've countersunk all those holes and the screw heads are now definitely below the surface there, which is what I wanted. I think that looks a bit neater, having the counterbore's a bit bigger too. So let's see how we went with the fit. Now remember, I had no dimension drawings to work from when I was laying out the hole positions in this part. The best I could do is sort of put the screws into the threaded holes and then get a pair of calipers and start measuring centre to centre distances. And I was sort of hoping that Colchester would have used, whole inch dimensions, or at least fractional inch dimensions across there. So when I got the measurements in metric, I just converted to imperial to see whether I was close. It looks like I got it right. So those two are good. That one's running in nicely. That one's just a fraction tighter, but it's screwing down okay. So there we go. That's going to give us a really nice solid base now for our parting tool holder. And as I said before, I could literally take this and put it at the front of the cross slide if I wanted to, and turn this into a solid tool post. Now, I think I'm at my half-hour limit, or probably over it. When we come back in the next video, I'm going to cut a big T-slot through here. I'm going to take a big chamfer off the front and the back of those long edges there. That's just to make it visually a little bit more appealing, but also if we're turning large diameter work, I don't want to run into that sharp edge there. So that's all going to be in the next video, but I'm going to edit this together. I've got a bit more time left over. We'll do the chamfers, but if not, you'll see that in the next video. So it's Prezzo. I'm going to sign out here now, just in case. I hate this. I hate sort of trying to guess how much time you've got and then do the sign off, and then sometimes you find out you're way over time, or you're way under. Anyway, I'm going to sign off now. We'll see how we went, and I'll check on the next video, and it's going to be part 2 of the rear parting tool holder build. Okay, cheers, see you next time.